Swayam Prabha. Digital India. Educated India.
So, we will start today with 2D NMR spectroscopy for heteronuclei. So, we have looked in the last class on how homonuclear spectra, what are the different types such as 2D toxi, 2D cozy and 2D nosy. So, that was in both the axes, it was hydrogens, protons and protons. Now, we will move on to if one of the axes is carbon, that means we are going to look at correlation between a carbon and a proton. So, that is why it is called as 2D heteronuclear NMR. Heteronucleus means two different nuclei. So, let us see how heteronuclear experiments are required. So, this is a table here which shows the different isotopes of different elements and their natural abundance. And the shown here is the spin value and frequency. So, based on the magnetic field, depending on the magnetic field there is a particular frequency, and shown here is the gyromagnetic ratio and the relative sensitivity. So, let us analyze this table a bit before we go to why we need 2D NMR or 2D heteronuclear NMR. You can see here for proton, which is the maximum having the 100% abundance, has a maximum gyromagnetic ratio, and therefore, it is the most sensitive nucleus in the whole of NMR spectroscopy. So, therefore, we normalize or we grade all the other nuclei with respect to the hydrogen. So, hydrogen will give it as 1, relative sensitivity as 1, and you can see here so for a given magnetic field, let us say it is 100 megahertz is the proton frequency. Now, if you start looking at the other nuclei with respect to the hydrogen, now you can see that deuterium has a very low sensitivity. You can see the natural abundance is very less, is only about 1.6%, and this is actually in the percentage. So, it is only 0.016%, and it is 6.5 times less in gyromagnetic ratio. So, therefore, if you calculate your magnetic field the frequency will be 15 megahertz. So, therefore, relative sensitivity based on these two factors. So, what has been done here is you multiply this factor, that is natural abundance, into the gamma, and then respects to proton. So, scale it with respect to proton, and then you can get the value of sensitivity. So, for example, for deuterium, if you multiply these two, it turns out to be 0.01 times 1, that means it is 0.01 or 100 times less than hydrogen approximately. Now, let us look at carbon, which is a very popular nucleus in NMR. So, the natural abundance of carbon 13, we have seen this earlier, is only about 1%. That means 99% of the carbon in any molecule, if you take a collection of molecules, is C12, and if you look at the gyromagnetic ratio, is about 4 times less compared to hydrogen. So, therefore, if you multiply these two, we basically see that is about 1.6 or 0.16 times of that of proton. So, that is a very low sensitivity because we have 100 times 4. So, it is about 400 times less, and remember we are going to detect both proton and carbon, we detect and excite nucleus. So, if you want to excite carbon and detect carbon, you have to have multiply gamma into gamma. So, 16 times it is less sensitive, plus there is a factor of 100 further because of the low abundance. So, that comes to about 0.016 times less compared to proton. So, this is a very low factor. In fact, you will need about 60 times more, proton is sensitive compared to carbon. So, this is why carbon sensitivity is low, and we need to do something more to increase the sensitivity. So, direct carbon experiment, therefore, we saw in the previous classes that direct carbon 1D is not a good idea if your sample sensitivity is low. So, there are varieties of methods which have been implemented, which are known to increase the sensitivity of carbon and other heteronuclei based on these factors. So, like this we can go on for different nuclei and see what is the different problems and why they are less sensitive and so on. So, you can see this is for fluorine is actually a very sensitive nucleus, it is almost as much as hydrogen. So, the sensitivity is good because it is almost 100% abundance, and the gyromagnetic ratio you see is almost close to proton. So, therefore, the sensitivity wise it is very close to proton. So, next to proton in the whole of periodic table, fluorine is the most sensitive nucleus, but our focus now will be only on carbon 13, because carbon 13 is the most popular nucleus and it helps a lot very much in getting the structural information of molecules. So, let us look at how proton carbon 2D experiments can be done and how we can improve the sensitivity of carbon, so that the sensitivity can be the spectrum can be recorded in a reasonable amount of time. So, these are the basically three problems which do not favor many nuclei. So, one of the most important two factors as we saw is gamma value and natural abundance. Natural abundance, if it is low, then sensitivity is less, and gamma, if it is low, the sensitivity is also low. So, compared to proton, these are the factors which make it less sensitive for X nuclei. So, in NMR typically we use this notation, we will say X nuclei or X nucleus to denote a nucleus which is other than hydrogen. So, this is a convention used, and also sometimes many of these nuclei have less favorable relaxation properties. That means the relaxation values are very short. For example, if you look at nitrogen 14, the spin value is 1. Similarly, if you look at deuterium, the spin value is 1. So, these are called quadrupolar nuclei, and for quadrupolar nuclei you have additional source of relaxation, and that reduces the T2 and T1 of these systems and makes it less favorable to study by NMR. So, for as far as spin halves are concerned, the additional source of relaxation can be what is called chemical shift anisotropy. So, chemical shift anisotropy is very high for fluorine and phosphorus. So, therefore, these type of nuclei are insensitive not only because of this problem, natural abundance or gamma, but also because of this favorable relaxation, less favorable relaxation properties. In fact, if you see for fluorine and phosphorus, abundance is 100%, but still we do not use them very often because of this additional problem of CSA induced relaxation even in the liquid state, and that scales we say with magnetic field. So, as you go to higher magnetic field, it becomes less favorable even more compared to low magnetic field. For example, for phosphorus one does not go beyond 500 megahertz spectrometer because the CSA induced relaxation is very high, and similar is the case with fluorine and nitrogen 15. So, we will not take into account worry about relaxation today or now in this heteronuclear. We are going to focus only on the carbon, because by far carbon is the most next favorite nucleus after proton in for obtaining structural information. So, we will stick to the in this whole course on primarily on proton and carbon. So, let us see how we can improve this. So, that is the reason, as I said, because of this unfavorable properties in the nucleus, the detection is very insensitive. Now, let us quantify that how much is the less sensitivity of this nuclei, how less is the sensitivity. Okay. So, how do we get this information from, how do we know that the sensitivity is less, why it is less, and that basically comes from this Boltzmann principle. So, this is what we saw in the very first part of the course. We looked at this energy levels and we saw that the population is distributed between these two energy levels. This is called the lower state or alpha state, the spin half, positive half, and this is for spin value minus half, we call it as upper state. So, the energy gap between these two energy levels is given by this equation. The delta E is gamma into H cross into B. So, this is what we have seen earlier. So, this is more like a refresher for that part. So, let us look at a little bit of some algebra here. So, if you go to the Boltzmann law, according to the Boltzmann law, the ratio of number of molecules which are sitting or which are located or which are here in the upper state, that is with spin minus half value, compared to what is in the lower state, if you look at this ratio, this is related to this expression given by this expression. So, here if you see Here what are the values? One is gamma, this is a constant, H is H, Planck's constant, this is B0 and this is Boltzmann constant and T. So, now typically what happens is the temperature that we work at in our laboratory is typically the room temperature, or you may go down to probably up to 0 degrees, but very rarely you go to very low temperatures of the order of like 100 Kelvin or even 5 Kelvin, 10 Kelvin. So, we are working basically at an ambient temperature conditions. So, under those conditions one can actually approximate this equation and write it in this form. Okay. So, this is called as high temperature approximation. The idea is the temperature we are working is at high temperature. Remember, it does not mean high means very high in the normal sense, it is even the room temperature is high enough. So, that if you take this quantity gamma H cross B0 divided by KT, this quantity becomes very small, and according to mathematical rules, if e raised to minus x is, if x is small where x is this number, then we can write that it as 1 minus x. So, 1 minus x where x is this number, which is what we saw. So, this is an approximation and we usually use the word high temperature approximation to denote this expression. Now, if you see here further, let us say I just do some little bit of algebra which will not go in detail, but if you do a little bit of rearrangement of this equation, you will see that this term can be now defined. So, what we will do is we will define, means we will say that there is a term called polarization. Polarization, we will define this term polarization now. Polarization is given by this expression n upper minus n lower divided by the total number of nuclei. So, this is the total number. If you add what is on the top and what is added on the bottom, that is the total number. So, total number basically means the total number of atoms in your sample. Okay. So, that is given a sample, I have a total number of atoms. So, when I put it in a magnetic field, some atoms will go to the lower state, some nuclei, and some nucleus of the atom go to the upper state in the energy levels. So, this is what we saw, this is a distribution. So, this if you add up the total value, that is the total number of nucleus, that is what is written as n total, and the difference in this population between the lower and the upper state, this difference is written here. So, this term, the difference divided by the total number is given, is denoted as polarization. Now, the polarization, this value can be obtained from this equation by a simple rearrangement. So, that is what is shown next, that if I combine equation 1 and 2 and do a little bit of rearrangement, I will get like this. Okay. So, this is something which I would encourage you to do it yourself and then figure this out, because this is a simple rearrangement of this equation, and what basically it says now is that the polarization means the difference in the population, which is what we saw here, is proportional to this value, this term. Okay. So, this is what it means. So, now you can see here this polarization is directly proportional to the gamma, okay, proportional directly to the magnetic field, and inversely proportional to temperature. Okay. So, these are the things which, if we know that magnet polarization is proportional to these factors, then we can do something to enhance. Our goal, as is said here, is how do we enhance the sensitivity of X nuclei. So, from here you can see why is the X nuclei less sensitive? The X nuclei is less sensitive because of the following. What is happening is, in the case of carbon, okay, so if you look at this term now, so we have a hydrogen spin level, energy levels. Now, hydrogen energy levels is given like this, and this is delta E is gamma H B0, which is we saw in the last slide. Now, if you translate or if you move this picture to carbon, you can see in carbon case what will happen. In the case of carbon, all other factors are same except gamma. So, in carbon the gamma is 4 times less compared to hydrogen. Therefore, the population difference will now be, as we saw in the previous slide, the population difference is proportional directly to gamma. So, if the gamma is 4 times less in carbon compared to hydrogen, then the population also will be 4 times population difference will also be 4 times less here compared to what you see here. So, this is schematically shown here. You can see the difference in number of spins is 8 and here it is 2. Okay. So, 2 is 4 times less compared to 8. That means the difference, if you subtract the number of atoms in the ground state minus number of atoms in the upper state, this difference is proportional to gamma. So, therefore, in the case of carbon it will be 4 times less, the difference will be 4 times less compared to difference here. So, please keep in mind this is just a notation and this is just a schematic, in the sense it is not that in reality there is a difference of 8 atoms, but the proportionality is same. So, whatever will be the difference in protons, carbon will be 4 times less. So, what is the importance of this polarization, this difference? The reason is that the sensitivity, that means how much signal you get in NMR, is directly proportional to polarization. So, this is very important. So, if your polarization is 4 times less for carbon compared to proton, so the signal also will be 4 times less in carbon compared to proton for the same concentration, for the same magnetic field at the same temperature. Keeping all other factors same, the polarization difference, a polarization which is population difference, is directly related to the signal intensity. So, from this you can see that the carbon is 4 times less compared to proton because of this reason. So, therefore, how can we improve the sensitivity of the X nuclei? So, one option is we can transfer this polarization from here to carbon to proton, so sorry, from proton to carbon. If we can do that, then the polarization of carbon is enhanced, and if polarization of carbon is enhanced, our sensitivity also is enhanced. So, this is basically like saying that suppose I have 1000 rupees with me and I have a person who is having 250 rupees, 4 times less, I can make the other person have more money by simply transferring the money from my side to his side. So, I can give 1000 rupees to him, so he will have 1000 plus 250. So, you see by doing that I can transfer the polarization. If I do that, then he will be richer. So, in similar way, if I transfer the polarization from a higher gamma nucleus to a lower gamma nucleus, then I will get the sensitivity enhancement of the lower gamma nucleus by a factor of 4 in this case, but higher factor in case of nitrogen and depending on the gamma value. So, this is the basic philosophy or idea in all the heteronuclear NMR experiments that we do in NMR spectroscopy, is that we basically enhance the sensitivity of X nuclei by implementing this concept of polarization transfer. So, polarization transfers can be done in many ways, but the basic idea is the population difference between one nucleus is communicated or transferred the population difference second nucleus, and the second nucleus now becomes as sensitive as the first nucleus, and then we can proceed further. So, this is basically how it is done. So, you can see now that the polarization in case after I transfer the polarization from proton to carbon, it will look something like this. What has happened? I have more nucleus now in the ground state compared to excited state, and the difference in the population is now as much as the difference which was here. But look carefully that energy levels have not changed. The gap in the energy level delta E, that is not going to change. Why? Because we have not changed the gamma value, we have not changed the B0 value, we have only transferred the populations like this. So, the energy gap remains the same. That means, carbon does not start behaving like hydrogen just because we transferred the polarization. The carbon remains as a carbon, only thing has happened is its population level, the difference has changed, and therefore, as to start with its sensitivity has gone up. Okay. So, this is the basic idea. When we start a heteronuclear NMR experiment, we first try to bring the polarization from the proton to carbon. We will see how we do that in different ways, and once we do that, then the population of carbon is high, difference is high. In such case, now the sensitivity will be also higher. So, what are the different ways we can do transfer this polarization? So, this is shown here as a scheme again in a words. So, this is what it says here, polarization transfers can happen through space interaction, which means, so you can look at this picture here, we are trying to achieve a transfer from hydrogen to carbon. Okay. So, let us say we have a molecule like this, where H is hydrogen is directly bonded, hydrogen is directly bonded to carbon. So, these two are very close in space, typically it is a one bond length. So, one bond distance in molecules is how much, is about 1 to 1.5 angstroms. So, in that distance I can use that short distance to, and these two, remember, both of them are spin half nuclei, means they are magnetically active nuclei. What it means? It means they have a dipole moment. This has a dipole moment, this one also has a dipole moment. Therefore, I can do a dipole, I can exploit the dipole interaction. So, there is a dipole to dipole interaction between these two nuclei, and that gives us a mechanism to transfer polarization from here to here. This is similar to what we saw in the NOSI experiment. So, similar idea we can use to transfer the polarization from here to here. So, this is typically what is implemented or used in solid state NMR. Okay. But if you come to solution state NMR, this dipolar couplings which we saw is not very strong mechanism to transfer energy. Therefore, we rely on a direct interaction through bond. So, you see this is a bond, is about one bond here, and that is there is a J coupling between this hydrogen and this carbon, and that J coupling will be used, can be used for transferring polarization from hydrogen to carbon. The typical value of J coupling is about 120 to 220 hertz. Remember, it depends on the hybridization state of the carbon. So, in aromatics it is higher, alkynes it is higher, alkene it is higher, but in sp3 it is about 120 to 140 hertz J coupling. So, this transfer of polarization using the J coupling through bond, you use the word inept. This stands for insensitive nuclear enhancement by polarization transfer. Okay. So, this is the typical word we use, inept. So, we will not go into detail of how inept achieves this polarization transfer. So, there is a mechanism by which you can use J coupling, but we will call this whole process as a single word, inept, and we say we will assume that by inept we can do this, achieve this transfer, which is possible. But how does an inept exactly work at a microscopic level, that part we cannot go into detail in this course. So, this is a typical step or method used in solution state NMR to transfer polarization from one nucleus to other nucleus. So, let us see schematically again how this whole thing is now inept is used for in 2D NMR heteronuclear NMR experiments. So, this is how schematically we can depict a heteronuclear experiment like this. So, what you can do, the block which I called as inept, let us assume that as a block, as a box, that is used first to transfer the polarization from proton to carbon. So, we will, as I said, this is not just a block like this, it is going to consist of a series of a sequence of pulses. A sequence of pulses together constitute a block which we call as inept. So, we will see the picture of inept a little bit later, but as I said, we will not go into detail of how this sequence of pulses achieve the transfer. So, let us assume that it does it somehow. So, this block of pulses I put it first. So, what will happen after the end of the block, the polarization from hydrogen would have been transferred to carbon. Then after that I excite the carbon by a 90-degree pulse, which is not shown, but let us say we have in this scheme a 90-degree pulse, and that excitation will bring now the difference of population from hydrogen of 2 protons. So, the population difference in carbon is much higher compared to what it was earlier. So, because of that, when I excite the carbon, its signal will be now 4 times stronger compared to not having this transfer. So, this is the advantage, your sensitivity has gone up by 4 times, which is a tremendous improvement compared to what if you did not have this transfer block or element. So, how does this 4 times sensitivity improve help us, we will see that later. So, this is one scheme of transferring the polarization. Now, if you see here, we are also writing here that you have to decouple proton when the carbon is running or when the carbon is acquired. Why is that so? That is because remember, whenever we acquire a carbon spectrum, we saw that earlier that it is J coupled to directly attached hydrogen. So, when I detect carbon, I should apply decoupling on protons to remove the J coupling, and therefore, the J coupling instead of coming as doublet, the peaks will come as singlets. So, that is why we decouple protons. Now, I can do this for a 2D. So, remember this will only gives me 1D NMR information. This is not a 2D experiment right now, it is still the 1D experiment, but the 1D, this experiment is different from the 1D we saw in the earlier part of this course, where we looked at 1D proton, 1D carbon NMR. There it was direct detection, means directly you start from carbon like a 1D proton, you like start from carbon and excite the carbon and detect carbon. But here we have added one extra step, that we first transfer the polarization from proton to carbon and then we detect the carbon. So, now let us see how it can be done in a 2D fashion. How can we convert this experiment into a 2D? So, this is how we can do as shown here. So, first apply a 90-degree pulse on hydrogen. So, this will be a proton. Okay, we will see this in a short while. This will be a proton pulse, not carbon. Okay, so, you apply this pulse on hydrogen proton, then the proton comes to the xy plane and it starts evolving because of the chemical shift. That means, it starts oscillating based on its chemical shift value, and that period during which it oscillates we call it as T1. Then you transfer the polarization to carbon. So, after evolution has happened for some duration, we will transfer that polarization to this, and after doing that polarization transfer, now after this step my magnetization has come here, it has come to carbon, and now I will excite the carbon with a pulse here, which is not shown, but it is part of this block, and when I apply a pulse, now the carbon comes into the xy plane and that is oscillating or moving or evolving with the chemical shift of carbon. So, this is the carbon detection experiment. So, what has happened? We have started from hydrogen, we evolved the hydrogen with its chemical shift, then transfer by polarization to carbon, then detected the carbon. So, now if you look at it mathematically, what has happened is the following: you start from proton, you transfer the magnetization. So, let us start from proton. So, we apply a proton pulse first, which is this pulse, and that will give me a frequency of proton during evolution, and that is denoted by cosine omega h T1, where omega h is the chemical shift of the hydrogen. Then we transferred the polarization to C13 and which detected the chemical shift of carbon, which I will call it as omega C or B. B is the sense second nucleus. Okay. So, this is how we get the transfer, and then now what you can see here, my FID finally will be a combination of this FID and this FID. So, when I combine, I am getting frequencies of proton which is now getting connected to or correlated to the frequency of the carbon. So, if I do a 2D Fourier transform like we saw in the standard in the homonuclear case, I will get now this spectrum, which is basically gives me a cross peak, and in one axis is proton and second axis is carbon. So, if you see here, what has happened is the proton is in the this axis y axis, which we call it as T1 dimension or F1, okay, whereas carbon has come to this axis which is T2 or F2. So, basically that comes from here. So, we have T1 proton along T1 and carbon along T2. So, this type of an experiment is called as 2D het core. 2D het core means heteronuclear correlation. So, 2D heteronuclear correlation was one of the beginning in the first experiments in heteronuclear NMR to be proposed, because there the idea was simply you transfer polarization and start detecting. But the problem with this experiment is that it is very less, sensitivity is low. And why is it low? It is because you are detecting carbon. Okay. We will see that how detection of carbon is not very preferable approach, the best approach would be to detect proton. Okay. So, you start from proton, you transfer to carbon and again come back to proton for detection. So, that instead of doing a detection of carbon, if I do a detection of proton, it is a preferable thing, but then that will not be possible using this approach. In this approach, I have to do the way it is shown here, that is I start from labeling or evolving proton and detect carbon. So, this approach leads to het core, but we will see in the next class that this is not the best approach, and therefore, for the best sensitivity it is better to start from proton and also end in proton, but at the same time get the 2D heteronuclear information. So, that is called inverse detection, and that will be we will see in the next class, because that will be seen as a much higher sensitivity than this approach of 2D het core.